All right, thank you very much. So yes, my name is Alen Stoyanov. I will be talking about a stage polymorphic IR for compiling MATLAB-style dynamic tensor expressions. So this work was done in collaboration with Tjerd Kronff from Purdue University and Markus Puschel from ETH Zurich. So let me start this presentation by, well, disseminating the title, particularly the part of stage polymorphic. So the first question is, well, what is staging? Well, staging is a special form of metaprogramming such that compilation is subdivided in phases, and each phase gets the input, the previous stage, and code is generated. In this talk, I will be focusing on a specific form of staging based on the lightweight modular staging done previously by Tjerd. The interesting part about this framework is that it does staging based on types, and how this thing works, we can illustrate it with this illustration. So if we have a simple function that adds two numbers, if the code is non-stage, once we invoke this function, what we're going to get is a normal CPU execution, and we're going to obtain the result back. If we stage the code, instead of having a normal execution, what we're going to get is a delayed execution, and instead of a result, an abstract syntax tree will be returned where we can play around with it. If you notice that the two versions, the only difference between the two is actually the type signature. So you can see that here in the add we have only floats, and here we have rep of float or representation of float. And as a consequence of that, what we have with this framework is staging based on types. So this technique is quite useful, particularly in the case when we want to build generators with it. And if we take again the same function, and let's assume that for a second we make it less optimized, having two ops. With the staging framework, we're going to obtain the AST. On this AST, we can perform optimizations and rewrites that can be domain-specific or low-level transformation, getting a more optimized AST. And once we have an optimized AST, we can unparse everything to a fast, performant, say, C code or whatever, or native code directly, or whatever we need. All right, so we get the idea of staging. Then the second part that I need to explain is what is stage polymorphism. To answer that is that, again, if we look at the same two functions that perform the addition, they look very similar between each other, the only difference being the type signature, right? But in reality, just because they're very similar, we can just simply merge them into a single implementation where the use of the stage or non-stage type is being abstracted as a type parameter. Since we're playing around in Scala, this can be a higher kind of type parameter that we pass into the function. So if we invoke the function with the identity type, what we're going to obtain is just a normal execution. And if we invoke everything with a type that we use for staging, or the rep type, we're going to obtain the stage version of the same function. Now, in world of Scala, we still need to get the implementation from somewhere. It has to come from somewhere. And in order for this thing to work, the actual implementation of what a plus operator does can be and has to be passed somehow to this function. And in order to do that, what we can do is we can use type classes where the implementation of what the plus denotes is encapsulated into this type class. In this particular case, we just have a numeric object that will define all the operation for a certain type T, regardless of whether this will be stage version or a non-stage version. All right, now this polymorphic representation does not really apply only to function. We can play around with other places in the code, and we have very interesting consequences of that. So one interesting part is that we can apply the same thing in for loops, particularly in Scala, since they are just comprehensions. So with this expression, if we initialize it with a rep parameter, what we're going to obtain is code that represents a loop. But in reality, if we put the identity type initializing this for loop, what we're going to obtain is unrolled code, because everything will be executed within this stage. As a consequence of that, optimizations such as unrolling can be simply encoded as type parameters within our implementation. Another very interesting consequence is that we can play the same tricks with arrays depending on where we put the higher kind of type, whether we put it in front of the array or within the array. So in the first case, if on front we have a wrap of array, what we're going to get is code that will generate array accesses, or we will have a representation of an array. If the representation is inside the array, we will not see an array in the generated code, but instead we're just going to see accesses to scalar operations. As a result of that, optimizations such as scalar replacement can be simply encoded as a type parameter. Finally, the thing that I mentioned previously with the numerics, they can also be used to abstract whether we're dealing with scalar instructions or vector instructions. So, well, if we want a scalar instruction, we just simply call the same plus operators. But if we want to do single instruction, multiple data vector type of instructions, we can just call a vectorized instructions on the same operations that we are using in the type class. The only difference between the two is whether we use a wrap of single instruction, single data, or scalar, and wrap of single instruction, multiple data type. So why is this important? Well, all this optimization or all this access of polymorphism, we can combine them in many different ways, and we can use them to create powerful abstractions. And to illustrate how useful this can be, consider just an addition operator that iterates through a vector. In this case, we just call it C vector, that has a bunch of parameters. We will not cover them in this case what every one of those mean, but in reality, we just iterate through the vector and we do point-wise addition. Depending on how we initialize this code with different kind of types, we can just obtain a loop that does exactly the same thing in terms of C code, or changing one parameter here, we're going to end up with unrolled code. If we want to vectorize code, again, we just put a SIMD parameter here and we obtain, say, AVX code. And finally, if we want to get the same thing and unroll it, we just change another argument and everything becomes unrolling. So with that, we can generate very useful code for numerical computations. We got to a conclusion, well, great. We have a tool for abstractions. Now let's build a MATLAB compiler because we can do it. Yeah. Well, okay, so things are not easy, right? So if you want to play around with MATLAB compiler, it's a little bit painful because it's typeless and it's dynamic, so everything can change at any point in time in the code. Types can change, shapes of tensor expressions can change in many different ways. And then furthermore, because MATLAB is built to be very easy and good for fast prototyping, many operators are overloaded many times. For example, a plus operator will work with two scalars, but it will work with two matrices with any kind of dimensions, and it will work again with a scalar plus a matrix. So technically, those are two very different operations if you think about it in terms of math, right? And finally, MathWorks, the company that is behind MATLAB, is continuously updating their functions, adding more functionality for one type or another type of dimensions, and so on and so forth. So as a consequence of this, as a consequence of the dynamism and the fact that it's typeless and overloaded, we haven't seen, well, a single compiler that even on a reduced sets will kind of cover all these dynamic aspects of the language. And then we ask the question, well, can we use this concept of stage polymorphism because it makes our life so much easier in abstracting things to actually get there? So we thought yes, but then again we have this problem, right? We want to do staging with types on a DSL or a language that doesn't have types. So this will be a little bit problematic, right? And the first question we ask, okay, we were talking about type classes, can we just play around with the same thing again? Well, the answer is no, because, well, if you play around with type classes, particularly in Scala, they require a type parameter that must be available at compile time of the Scala generator. So this is not something that we can work with because in MATLAB anything can change during runtime or during execution. So instead of this, we have to think about a way where for each variable, we represent the variable, but we also kind of pass its type. So we have to resort to type values instead. Now, if we want to do this, what LMS is offering or what we have is that things get, again, a little bit complicated. And the reason for that is that if we have a plus operator again, the one that we discussed before, suddenly if we want to include the type, things get complicated because it blows in parameters because we have to include the type. Now, we can take this and we can simplify with a very, very small trick, such that we put everything in a container that will represent the variable and its type. And then, of course, then the signature of what you represent as a plus becomes simplified. But in reality, we can just put both of those into a single container that include the type and the variable and create this abstraction that we decided to call a meta container. So this idea, and this abstraction, we will use later on in building our compiler. And the idea to define it properly or formally, for us, a meta container will be a runtime object wrapper for a given meta container reference. In this particular case, the variable that we represent, its metadata, namely the type or anything else, and all the routines associated with it, such as plus or any kind of operators that we have. Now, if we build abstraction based on these meta containers, then what we discussed about type classes, well, this can almost already offer a replacement for type classes because we can abstract on top of them. We can easily build complex numbers or real numbers and so on and so forth. And those can really specialize very easily on the type that we have, assuming at some point we have figured out the type. And of course, since we can implement different versions, again, these meta containers can as well be polymorphic. All right, so we get the notion of what meta container is. Now let's discuss how we can apply the abstraction of the meta container with our goal. To actually do that, we build a generator, and we called it mgen. And mgen will actually start with a MATLAB file, parse it. We did not do the parser. We use a previous work based on the timer tour from MCLab. We're going to obtain an AST that we will convert into our own high-level representation that we call MIR. The MIR will start with all input arguments annotation. So, for example, we can say that, okay, a certain function uses 2 or 3 arguments. We can say what types they are, or maybe what dimensions they have, or maybe we provide nothing, depending on what we want to achieve. The MIR will do a set of standard optimization. We will convert everything to SSA, perform dead code removal, common sub-expression elimination, and so on and so forth. And then, since we don't get nothing out of the MATLAB code itself, but the language, we have to do the shape inference, where we have to infer as much as we can the types, the complex types, dimensions of tensors, and so on and so forth. Once we're done with that process, we'll lower everything down to a CIR, low-level representation, where we specialize the code on the types that we have inferred. We lower the operators, and ideally, we specialize to a given ISA on a machine and perform explicit vectorization. Finally, the result is a C code generated out of the same MATLAB representation. But let's to discuss about this, let's see what we are dealing with and what are the challenges. So in MATLAB, if we have a certain variable, we just so every variable is could be multi-dimensional. It can have multiple dimensions, or it can be a tensor. And for each variable, we just have a representation of a tensor that we call shape in our case. Now, tensors can either be provided as arguments to functions, or they can be result of computations. Each tensor can be, as I said, well, scalar, matrix, vector, multidimensional matrix, and so on. Can be real or complex, and can be one of the 12 primitive types that MATLAB is supporting. This is like float, double, integers, longs, unsigned, signed, and so forth. This applies obviously for every single variable. And the interesting part is that the result in this, from this operation, actually the operation itself dictates the result of what kind of shape the next tensor is going to get. So in other words, I mean the same thing applies for the types, or in other words, the tensor metadata that represents this tensor propagates through the code or through the expression that we have in MATLAB. As a result of that, to keep track on everything, we use the previously mentioned meta-container abstraction, where for each shape, we create these meta-containers that they will reason about dimensions, about its types, complex types, and so on and so forth. Notice this transfer method. We're going to mention this a little bit later on. So once we have that, the first question is, okay, how do we actually do type inference? Well, for type inference, first we have to know what MATLAB does. And this can be somewhat complicated because MATLAB has different kind of type rules which are not always standard. And in order to do that, what we did is like we went in MATLAB, we created small functions that include the operators for 2, 3, or n array operations, and we just brute force them with all operations. If the operation is successful, or in other words, if we have no exception, this means that the operation succeeded and this type combination is possible. So out of this, we actually created type rules for each supported operator. And for example, for the plus operator, we can see a double times double gets a double. And since it's MATLAB, if you do double an integer, you get an integer. It's a little bit, it's a little bit weird. They play around with something that is called saturation arithmetic, so nothing will overflow in MATLAB, and this is why we have that. And in reality, just a simple plus operator will result to 56 different type rules. So once we do this for every function that we support, and once we're done with that, we just go back to our MIR, we just perform data flow analysis, we apply each rule at each point in the code, and we infer the types, and once we're done with that, we store the results in the meta container. So relatively simple, and we kind of have to do the same trick to infer dimensions, but it gets a little bit more fun here. So shape inference, I will illustrate this through an example. So consider a Fibonacci. In this particular case, it's just an iterative Fibonacci example. We have, well, 2 mutable variables and a for loop that just updates these variables. If we convert it into MIR, or elements representation, we're going to obtain a graph that looks like this. So the mutable variables are the triangles. They get read, they get updated, and the process continues, everything in a for loop. Now, in order to infer the dimensions, what we start to do is that we start injecting nodes, creating an overlay IR, and for that, we create a meta container for each variable that we have, and inside the meta container, we'll create the objects that represent the dimensions. We continue doing this iteratively at each node into our MIR till the moment that we complete the whole overlaid IR that represents dimension operations. Now, the interesting part, what happens later on, is that since we build this new IR, basically all the nodes that reason about the dimensions are injected, right? But then, at the same time, all the parts of this meta containers are exposed, and we can even drop the meta container completely and disregard all MATLAB operations. So in reality, with this process, we can separate all MATLAB computation from the computation that actually reasons about the dimensions. As a consequence of that, we get a simplified overlaid IR that it's much easier to analyze in order to infer dimensions. So since we were dealing with Fibonacci, in the next step, we perform constant propagation. Since it's Fibonacci, everything will be scalar in this case, and we will obtain a list of required substitutions for each dimensions at each step. And then the previous mentioned transfer method will take this substitution and apply them back to each meta container. This process will result in specializing each meta container to obtain the dimensions and the type at each point in time. To kind of illustrate how this process looks like, if we start with Fibonacci, in the step of inferring dimensions, we explode in a code like that. You don't have to focus what this code does. but briefly I can mention. So there is code that will inspect the dimensions and check whether this is a valid operation. There will be another code that will care about the overridden operators. So is this a scalar plus a multidimensional matrix or multidimensional matrix with the same set of dimensions? And once we are done with this process, once constant propagation finishes, everything will be optimized here and specialized, and we're going to obtain an IR that knows the types, that knows the dimensions at each point in time. So to summarize with this process, what we have three things that we do. The injection of nodes with the meta containers will simplify the construction of the DSL. The expose and separate process will simplify our analysis because we only analyze the overlaid IR. And finally, the specialization will simplify vastly transformations because instead of performing complicated rewrites, we only have to just specialize the meta container in order to know what we are dealing with. And with that, we are capable of completing every information that we can at the higher level MIR. And the next step is to take the MII and convert it into a CAR lower level representation. Well, I mean, the way how it works is that on the MIR level, of course, everything is a meta container. We do the same trick for meta containers, even for the dimension arrays. They get also specialized. And once we go down to CAR, for each shape, we specialize it into C shape that cares about memory location, whether something is input or output or intermediate representation. And once we have specialized the memory locations, we specialize into so-called C array, where the type is specialized, so we know everything about this array. And in our case, the C array is similar to this C vector that I mentioned before, where we could unroll and vectorize everything. So they are almost equivalent. And this is how we can get explicit vectorization and all this information that I discussed before in a way for free, right? So with that, we are capable of generating C code, and we're kind of done with this process. So how good is this method? Well, this gets us to the evaluation. And we took our code and we compared it against the MATLAB coder, which is proprietary implementation of MATLAB. Then Amadeus, an MCLab, Tamer, and two of its backends, where all those are open source projects. So we are very good when we have to infer all the types because of these rules. We are very good in inferring the shapes in all cases that we tested. And we can handle many overloaded built-in functions that the language is providing. We can also provide complete implementation of all arithmetic operations because we can specialize on all type combinations. We can handle the saturated arithmetics, this integer plus double. And we can do explicit vectorization. The things we haven't done yet in order to get the highest performance is still we don't do range analysis, where we can think about, escape analysis or many other things that are important. And we haven't done the memory optimizations. So while this is very good in these parts, the memory optimizations are the reason why for performance we are still not there. And to illustrate how bad this can get for memory optimization, I provide this small example where we do a gradient descent. And the gradient descent is done on one matrix and a vector. And the graph here represents, on x-axis, we get the sizes of the matrix, and on the y-axis, we get the performance in flops per cycle. And what we got, we compared this against MATLAB Coder and the MATLAB VM. And so far, MGen, you can see that it's almost like it's the slowest, and it's a clear line without any bumps. So we are memory bound in this case, and this is why optimization is not done. The moment memory optimizations are implemented, we might have much better results. So with this, I kind of conclude the result. And as a summary, what I was discussing about was meta containers as an abstraction that will just simplify our life in constructing the DSL and analyzing it and transforming it. And to illustrate how this works, I was talking about a prototypical MATLAB-like generator for tensor expressions. Thank you very much. Yeah.
So, seems like how well your frameworks
Of course.
And then obviously in some cases you will not infer good reference results, and so your compiler will deliver poor performance.
Exactly.
How am I, as someone who uses your compiler, going to know what's going on?
That's a good question.
Because the nice thing about staging, as you normally do it, is that you know precisely what's going to happen because you put the annotations in there.
Mm-hmm.
You know what's going to happen. It's very predictable. Here you're sort of into sort of an unpredictable thing that where you're stating annotations. I mean, they're nice for implementing it, but I think we're missing out on the more predictable parts.
Yes. So, I mean, in principle, you can even write by yourself pathological cases where the compiler just cannot infer stuff. I mean, even the best of inference algorithms will lead you maybe two paths that merge at one point that might have different kind of shapes and even different type, right?
Yes.
Now you're generating C code, right? And you need to be able to handle this statically, right? So in that particular case, you have to write code that will perform type inspection and generate the two versions. And basically, if you want to generate C code, there is no way you escape this thing, right? Now, the question is how the developer that is using this can actually be aware of that. Well, we can implement something that just gives a trigger, maybe at line this, you have multiple types and error happens, right? Or maybe just write your code or give a suggestion, write your code in a different way. With the staging process, we know exactly at what point in time in the code, because the MIR IR is more or less equivalent to the MATLAB code, except that it's SSA, right? So you can say, look, at that line, this is a problem, maybe write your code in a different way, or even just produce a list of what the inference has actually inferred, right? So this could be one option. If you compare it with what, say, the MATLAB coder is doing, is that in some cases, because it cannot really do type inference, it just fails and says like line so and so, we cannot support it, and that's it, right? So at least in this case, we can just produce some code, right, that is correct, might be slow, but it also depends, you know, on the MATLAB developer to actually write it in a nice way.
Okay, thanks.
Other questions? Just a quick question. Your target one is MATLAB. Oh, can you take your microphone?
Yeah.
To the second speaker. So your target language